Hello. Today we're going to be looking at the analysis of covariance, but let's just briefly revise where we've got to so far. Early on we looked at the approach of linear regression, in which we have a continuous response variable and we related it to the size of a continuous predictor. And the way we did it is we fitted a linear model to our data to see whether we could reject the null hypothesis that the true gradient at population level was 0. And we can also ask questions about the intercept. We've also looked at a related technique where instead of a continuous predictor, we've got a categorical predictor, and here we have one with two separate levels for that single categorical predictor. And we wanted to know whether the size of a continuous response was in any way related to the levels of that categorical predictor, and this is the type of model we fitted. This is the analysis of variance model. What we're going to be looking at today is a combination of linear regression, in which we've got a continuous predictor, and analysis of variance, in which we've got a categorical predictor. And here is what it looks like in its simplest form. Here we have a continuous response related to the levels of a categorical predictor and also the size of a continuous predictor. It's a general linear model, very much like linear regression and analysis of variance, and so we make the same sorts of assumptions about the nature of the error term, i.e. that it's normally distributed, and fixed variance for whatever level of predictors we're dealing with. So in essence, what we are doing here in the simplest form of analysis of covariance is fitting parallel lines, the difference between these lines representing the difference of the treatments, and the gradients of the lines themselves representing the influence of the continuous predictor. So in words, we can have, for example, a continuous response like weight being related to the size of a continuous predictor, like the size of one's right leg, and a categorical predictor, for example, one's gender. Or the volume of a tree might be related to the height of that tree, which is continuous, and the type of fertilizer it's received as it's been growing. Here are the equations representing a simple analysis of covariance. It's a simple equation. Here we have the continuous response, there's the continuous predictor, and here are the levels of the categorical predictor with the inevitable epsilon, the error, the part that of the variability of the data that the model cannot explain. We'll have a look at the leprosy example in a lot of detail in the practice and also on the website, but here for now I'm just going to introduce the concepts. This is a really nice data set which came from Graffen and Hales. It's modern statistics for the life sciences, and it's a data set relating to the bacillus scores of leprosy patients before and after treatment. Leprosy is of course caused by a bacillus, and in some way they've managed to measure the bacillus scores of patients before and after treatments. There's three different drug treatments that they have received, 1, 2 and 3, and here are the data listed. Now what we really want to do is to have a look at the bacillus score after, but that might be related to two separate things. One might be the bacillus score before, because if you start with little, you might end with little. Likewise, if you start with a lot, you might end with a lot. But also the treatment, and this is what we're particularly interested in evaluating, whether there's any evidence of a treatment effect. That's the Wirt equation, and here's the type of model that we would be fitting. This is the bacillus after, this is the bacillus before, and it's a continuous predictor, i.e. a covariate, and we might be estimating a gradient here, and here are the adjustments according to the different levels, different types of that drug treatment. Here are the data plotted out, and in the practice part you'll see just how to plot these data out with the legend there in the left hand side. This is the bacillus before and bacillus after. So it really does look like that there is a relationship between bacillus after and bacillus before, but can we actually within these data see any evidence of a treatment effect in alleviating the bacillus? So here's the type of model that we'd be fitting in an analysis of covariance. There's the bacillus after related to the bacillus before, and just because we've coded treatment as 1, 2 or 3, and to ensure that R treats it as a categorical factor rather than a covariate, we're saying factor here, and this is where the data are coming from, and this is what the output is of a fitted general linear model. We can see two things. The first is that the bacillus before explains a high degree of variability in the bacillus after, in that we have a highly significant effect of bacillus before on bacillus after. However, if we were to use the threshold of 5%, we don't really have very strong evidence to reject the null hypothesis that there is no effect of the factor, i.e. the drug, on the bacillus after once you control for bacillus before. You'll note that this is a type 1 sum of squares by default, and so with this second term here we're actually controlling for the covariate when examining the effect of the treatment. In the practice we'll look at a whole variety of different forms of breaking down this variability, including a type 3 sum of squares, but that will be later. Let's have a look at the model coefficients. We can simply call up coef for that model 1, and here is the reconstructed model based on those coefficients. Here we've got an intercept of minus 1.603, there's the gradient, and then we have a degree of aliasing. The first treatment level is actually incorporated, subsumed within the intercept, so we've only got treatment levels 2 and 3, which is why they're listed out here. That's the best fit equation. Now, using R, we can actually draw out this relationship here, and this is what we get. Clearly, what we have done here in the simple forms of analysis of covariance is that we have fitted parallel lines. These differences, whether they're significant or not, representing differences between the treatments, and the overall gradient representing a relationship between the bacillus before and the bacillus after. Of course, we should check our residuals to ensure that the fitted model is as appropriate as it could be, and here we have a pretty good case. The residuals appear relatively homogeneous for different levels of the predictor, and also relatively straight line when we plot the QQ plot. So this is what we have so far. We fitted models with a predictor which is both continuous here and categorical, and here is the outcome in terms of the fitted model. But wouldn't it be nice to be able to fit on occasion models in which the lines are not constrained to be parallel? Well, of course we can do this easily by simply specifying a rather different fitted general linear model. What would that model look like? Well, at its simplest form, it would be of this type here, where we have the beta times back before, as always. We have the treatment level adjustment, but then also we have what's called an interaction between the categorical variable and the continuous variable. So, for example, we've got gamma 4 for treatment 1 times back before, when added to the beta coefficient would change the overall gradient just for that individual treatment, and so on. So we can easily specify a model on which there's a different gradient for each treatment level by inserting an interaction. How would we do that in R? Well, it's very straightforward in R. Here is a fitted model, not just the additive terms between back before and the factor, but also we have a multiplicative form here. Now, by adding the interaction term there, R assumes that the main effects are already going to be there as well. So we will look at the separate terms as well as the interaction when fitted that model. And here is the overarching analysis of variance model with a type 1 sum of squares. What can we conclude from this? Well, I find it's useful to work from bottom up, beginning with interactions and then moving up through the different levels, particularly when dealing with a type 1 sum of squares where order really does matter. So there's no evidence for a significant interactive effect in that here we have a value which is relatively high, so we're not really rejecting the null hypothesis there. There's also no evidence for an effect of treatment once a back before is controlled for, because you'll notice in a type 1 we're controlling for things above it in the list, and here there is no effect of that treatment just as before when we control for back before, and yet there remains a very strong effect of back before on a back after. And the overall fitted model actually looks like this, and we'll see how to fit such graphs in the practice and web parts of this particular application. Thank you for listening to this R Labs tutorial video. If you found this useful, you might be interested in our free online Moodle course, or check out and subscribe to our YouTube channel.